Hello everybody, welcome to another video lesson. Today we're going to look at dot products of vectors. After this lesson, we should be able to find the dot product of two vectors and use the dot product to find the angle between those two vectors as well. So let's hop right into our concepts for this video. Our dot products, okay, what are the dot products? We want to think sort of like directional multiplication, okay? We are applying the directional growth of one vector onto another, okay? And notice the directional in both of these, okay? Directional multiplication, directional growth, okay? So we've got the result is really how much stronger we've made our original vector, all right? So we've got a dot b here, and we need to ask how much energy, right, or push is one vector giving the other, and in a specific direction as well, okay? So let's think about here, we've got our vectors a and b. Say I took the dot product of a and b, and we would refer to that as a dot b, and I'll go over that again at the end here. But let's think of this as the horizontal component affecting A, affecting the horizontal component of B, okay? And how is that affecting that component? Plus, we've got the vertical component of A, and how is that affecting the vertical component of B? Again, you can take both of these vectors and we can express them in vertical and horizontal components, okay, horizontal component of B and the vertical component of B as well. That's what we're looking at down here with this dot product. Okay, and then we're adding again, we've got the horizontal component of A, and how is that affecting the vertical component of B? And then one last thing, we've also got the vertical component of both of them. How are they affecting each other? How is this vertical component of A affecting the vertical component of B, okay? And this kind of, as a whole, gives us what's going on with our dot product, all right? So now, I've got up here orthogonal vectors have a dot product that's equal to 0, and we'll go over kind of what that means here at the end of this slide. Okay, so we know based off of this setup here, I've got vector A, vector B, and then a resultant vector AB. So we've got the absolute, sorry, not the absolute value, we've got the magnitude of vector AB, okay? And I guess this isn't necessarily the resultant vector, but you could think of it as the resultant vector because you would go tip to tail, right? But yeah, we've got the magnitude of AB, okay, and that's equal to the magnitude of A squared plus magnitude of B squared. Okay, so this sum right here is the magnitude of AB squared. All right, and we can kind of see that just based off of our Pythagorean theorem, right? We've got a right triangle here. Okay, so we got one leg squared plus the other leg squared. That's going to be our hypotenuse squared, which is vector AB. Okay, so if I wanted to find just the magnitude of AB, not the magnitude of AB squared, I would take the square root of both sides. But what is the magnitude of A? And what's the magnitude of B? Well, we've seen this before with our, we just need some coordinates in here. So if this is point A, and that has the point A1, A2, and point B down here has points B1, B2, then what would go inside of here, knowing that that is the initial and terminal points of AB, right? That's going to be the difference in the x direction, so B1 minus A1, plus the difference in the y direction, or the vertical direction, that's going to be B2 minus A2, and both of those quantities are squared in there, okay? So let's go ahead. We're going to prove that this is equal to something very similar, and we'll go ahead and take the, we'll square both sides, all right, and then what we get is a couple of squared terms here, and we're going to go ahead and expand those. Okay, and when we do that, we're going to then add our b1 squared plus b2 squared and a1 squared plus a2 squared. Why are we doing that? Well, because remember the magnitude of a vector is equal to the square root of its first component squared plus the second component squared. Okay, so if we took the, if we squared both sides down here, we would get a1 squared plus a2 squared, which is exactly what we have right here. And likewise for b right here. So what these two terms actually say, these are actually the magnitude of a squared plus the magnitude of b squared, okay? And I just flipped those, but that is exactly what's going on here. But we also have this term right here, which you'll notice makes these two expressions or these two equations not equal to each other, right? And that is unless what? Unless this term down here, okay, this a1b1 plus a2b2, that would have to be 0, right? That would have to be 0. And this right here, a1b1 plus a2b2, that is actually our dot product, okay? Okay, so that is dot product, and you'll see that on the next slide. But what does orthogonal vectors mean? Orthogonal vectors are vectors that have a 90-degree angle in between them, like you see here with A and B. Okay, you might think of them as perpendicular vectors, but they have another name, that is orthogonal vectors, right? So our dot product again is a1b1 plus a2b2. So again, I'm going to bring up our other vectors a and b from a couple slides ago, and we've got exactly what's going on here with our dot product. We've got the changes that a is making on b in each direction, okay? But I want you to focus on these middle two here, okay? Because how is the vertical component of a affecting the horizontal component of b? Is it helping this grow, or is it compressing it at all in the x direction? Hopefully you can see that for both of these middle ones, since they are at a 90-degree angle, right, they are actually not affecting each other at all, okay? There is zero sort of influence from the vertical component of A onto the horizontal component of B, okay? And there's zero influence from the horizontal component of A to the vertical component of B, right? There just is no influence. We're not shrinking or growing these components, okay, because we have this push or pull in completely the 90-degree direction, okay? And so for our dot products, how you would see that, oh, and if we go ahead and, since those are 0, if we kind of finish out this semi-equation that we have going on, we've got a times, or ax times bx, okay, which is like a1, b1, plus ay, by, which is like our a2, b2 right here, okay? And how we would say this, okay, for our dot products, is we have some properties right here. So for this first one, our commutative property, we would say this u dot v, okay? U dot v and v dot u. That's how we say our dot products. So go ahead and write these properties down, all right? And we're going to go ahead and prove just this first one, and then you guys can just have the other ones to work with, all right? So we've got, if I've got u in component form here and v in component form, we're going to prove the commutative property that says u dot v should be equal to v dot u. All right, so u dot v, what is that going to be? If these are my components, well, that's going to be u1 v1 plus u2 v2. Okay, and the question is that equal to v dot u? Well, if we go ahead and take this dot product, you'll see that v1 u1 plus v2 u2, that is in fact equal to what we have over here on the left, so that property checks out, all right? Okay, one last concept slide, the angle between our vectors. We have a formula for that, and let's go ahead and find that formula. So to do that, we're going to need our law of cosines. Okay, hopefully you remember this from last unit, or maybe it was a couple units ago now. But we've got c squared plus a squared plus b squared, or c squared equals a squared plus b squared minus 2ab cosine of c. Okay, where c is the angle opposite of this side c. So in this case, what we have here, we've got this side, or this side here, the side AB, right, this vector AB. So we've got the magnitude of AB squared is going to be equal to the magnitude of A plus magnitude of B minus 2 magnitude of A, magnitude of B, times the cosine of theta. Okay, and again, theta is this angle opposite of AB here, all right? Okay, now, when we were proving what our dot product was, we said that the magnitude of AB squared was equal to this left-hand side of my equation now right here, right? where this part had to equal 0 if it was an orthogonal set of vectors, right? And that's going to be equal to, again, we haven't changed anything here on the right-hand side, okay? But we can start combining some like terms right now because my magnitude of a's and magnitudes of b's squared, since we have that on both left and right-hand side, those will cancel out. And we're left with this equation here, and we can divide by this -2 on both sides. And here's what we're left with. And hopefully you can see right here, again, we've got our dot product. Okay, so I'm just going to substitute a dot b for what we have here on the left. And when I solve for cosine, you get this equation here where cosine theta is equal to a dot b over the magnitude of a times the magnitude of b. Okay, so if you're ever asked to find the angle between two vectors, this would be the direction to go, all right? Okay, so let's get into some examples here. Find the dot product, determine if the vectors are orthogonal or not. All right, so u dot v, again, we are going to have u1 v1 plus u2 v2. So here are our components here. Okay, so 3 would be u1, -2 would be u2, and so on. So we just substitute those right in. So I've got 3 times -5 plus -2 times 1, and we get -15 minus 2, -17, which is not 0. That means it is not orthogonal. These vectors are not orthogonal. All right, same exact process over here. So you guys pause the video, see if you can't figure this out. And hopefully you got that these are orthogonal vectors as the dot product is 0. All right, now let's go ahead and find the magnitude using our dot product. If you remember from the properties slide, okay, we have that the magnitude squared is equal to the dot product of the vector with itself. Okay, so we would say a dot a. Okay, so the magnitude now, if we just take the square root of both of these, is going to be the square root of a dot a. Okay, so this being a1 and a2, we would just say a1, basically a1 squared plus a2 squared, take the square root of that whole thing. So that is going to be 12 squared plus 16 squared. That's going to be the square root of 400, which is 20. Okay, same thing over here with the vector d. We're just going to take the square root of a1 squared plus a2 squared. So that's going to be 1 plus 49, square root of 1 plus 49, square root of 50, which is going to simplify to 5 root 2. All right, last example slide. We're going to find the angles between the given vectors. So we're given these vectors in component form. And again, we just need to use our equation. Cosine theta is going to be a dot b over our magnitudes. In this case, it's going to be u dot v over our magnitudes. So u dot v looks like -3 times 2 plus -5 times -3. And then we're just using our magnitude relationship with our dot products, taking the square root of u dot u and v dot v for the numerator or for the denominator here. That's going to give us -6 plus 15 over root 34 times root 13. Just take the inverse cosine of both sides to find a theta that is approximately 64 degrees. All right, go ahead and use that exact same process over here on the right-hand side and see if you can find the angle between vectors u and v. Okay, so this is the process here. Again, we're just using our equation and filling it in. Kind of plug and play here, and then take the inverse cosine at the end, and you should get an angle of just over 147 degrees. All right, that is all we have for this video, you guys. Good luck with your practice.